Hey, welcome back. We're going to continue our discussion using polars and double integrals to find area and later, of course, volume. It will be somewhat useful to convert rectangular coordinates into polars than to just and then integrate. For example, we know that the equation of a circle given by x squared plus y squared equals r squared. If we had to choose to integrate x squared plus y squared or the r squared, of course the r squared is much easier to integrate. Now remember, the x squared plus y squared, that's our rectangular form. And the r squared, that's our polar form if we convert from what we learned back in pre-cal. So it's a lot easier to integrate r squared than the x squared plus y squared. We will, of course, have to define polar regions using r and theta. So let's take a look at how we can do that. Now, but first, let's take a look at this circle right here, or this chord of a circle. We're going to look at this rectangularly and then using polars, and you'll see the big difference. So when they find the intervals, so we're going to find the base. This is our base region on the xy plane. If we want to look at this rectangularly, we have to find out, well, what are the change in y values and what are the change in our x values. And we can do that. Let me dim it down a little bit here. And we can do that by looking at our rectangle of mathematics. There's my rectangle of mathematics. So I can get the top of this circle. This is just a circle right here. And that's going to be y equals the square root of 4 minus x squared. So I know that my change in y's are going to go from 0 to the square root of 4 minus x squared. My change in x's are going to go from 0 to 2. Now, if I try to integrate this, I would get my double integral, 0 to 2 for the x's, 0 to the square root of 4 minus x squared, dy dx. And it's not bad looking, but let's see what happens if we can do this in polars. Now, I'm going to do this one in red, okay? So in red, I'm going to do a polar. You might recall a polar is measured from the center, something that we call the pole, outwards. So there's my rectangle of mathematics, but this time it's out this way. So for polar, there are two things we have to look at. We have to look at the change in the radius and the change in theta. So the radius is right here. There's my radius. That's the length of it. And theta is just the angle that we are rotating. Well, let's see here. Well, what is the radius going from? Well, this is a circle. The radius is always going to go from 0 and go all the way out to 2. At the pole, the radius is 0. On the outermost, the radius is 2. So the radius just goes from 0 to 2. What about the change in theta? Now remember, we're going to be using radians. So we start at theta equals 0, way down here, and at the very top at 90 degrees, we got theta's pi over 2. So my change in theta goes from 0 to pi over 2. And if I want to write my area, it's going to be the double angle. And I'm going to do, now, you got to remember from our proof, right over here, is how we found that change in area. It was r dr d theta. If you didn't see that, go watch the other video number 1 on this one, and you'll see that, okay? All right, so here we have, this is going to be now r dr d theta. My change in r goes from 0 to 2. My change in theta, 0 to pi over 2. And this one looks slightly easier to integrate than our rectangular one up there. We don't have to deal with the square root mainly. Okay? So if we can convert circular bases to polar form, it does tend to make this a little bit easier. So let's take a look. Let's just see if we can find the polar for this one right over here, the polar limits for this next one. Go back to black. So if I want to find the limits here in polar form, again, I want to find the change in the radius and the change in theta. Theta should be pretty easy. if I draw my radial arm, now remember, in polar form, in polar, the radius is that radial arm from the center. In other words, from the center, I'm going to go out. Now this is going to be dashed because there's nothing there, but this part's going to be solid. So if I want to find the area here, there's my radius, here's my radius, here's my theta, right over here. Now remember, this is really my change in radius right here if you think about it, because it's the change where my radius goes outward from 1 all the way to 3. My theta, well, how is theta changing? That's my change in theta right here. From 0, and I'm going to go full circle, which is 2 pi. 0 to 2 pi. So if I want to find the area of this circle now, I'm going to use my formula, r dr d theta. This is our polar form. We'll talk about that again, how we got that, in case you missed it or had trouble with it. So we got r dr, I feel like a joke, r dr d theta. Yeah, I cracked myself up. My dr goes first, that's from 1 to 3, and my theta goes from 0 to 2 pi. And that would give us the area between those two, the area of the shaded region in those two circles. Alright, so let's take a look again about how we really kind of get this formula right here, r dr d theta. So it comes from this little piece right over here. So remember, so this is, we're looking at, as we move our radial arm, we hit here, and then we're going to hit over here. So in between there, it's sweeping out an area. You might recall that from calculus. So I want to find the area of this little region right here. We want to find the area of R. So to get area, I'm going to imagine theta going to the 0. Delta theta going to 0. So this change in theta going to 0. So we have two radii here. So we have this radius and this radius. There are two different radiuses. However, as theta goes to 0, these two lines, these two radial arms, become the same. In other words, that this length becomes this length. And we can call that delta R. That's my change in R. Well, what happens here? Well, as theta goes to 0, these two lengths also become the same. And that is just my arc length. That is just my arc length, S. Right there. So as theta goes to 0, a couple things happen. We're basically going to get a rectangle. One length being delta R, and the other one being my arc length. Well, how do we find arc length? That is just R times theta. Right there. So, but remember, theta is changing and going to 0. So I could write this as, this is all based on my change in theta as it goes to 0, so we can get S equals R d theta. So the area of my rectangle here would be R d theta, delta R. And as theta goes to 0, these become d's, and we're going to switch the order here, R dr d theta. And that is how we get our area. And that's where we got these little parts right up here. So today, we're going to discuss how to convert polar coordinates into rectangular coordinates into polar coordinates in order to integrate. But let's review a few little formulas. These are from pre-cal, where we have x equals r cosine theta, y equals r sine theta. This would be how we would convert polar to rectangular. And over here, x squared plus y squared is r squared. And to get the angle, we could do theta equals inverse tangent of y over x. And this would be how we would convert rectangular to polar. Alright, go on to the next video, and we're going to take a look at a few more examples. Okay, so I'll see you then. Bye-bye.